Today's lecture, we're going to talk a little bit about GIS of the future. Some of it's more like the present is beginning to expand because some of these things are starting to come about. And then we're gonna, since we're not gonna have a final review or a final exam, we're gonna review what did we learn this semester and try to spool through that fairly quickly. So you can have an overview to kind of cement everything in your head again. So last chance for questions before we start that. I will be in our lab session on Thursday. I'm not assigning anything new. I'm happy to go over any questions that you might have. And you can show up and work on final projects and see if you need any help with any of that. I apologize to anybody whose area I haven't added to the map. I haven't noticed any conflicts or problems, so consider yourself good to go if you hadn't already decided that. So I'm not going to get heavily into accuracy standards. A lot of the way accuracy is controlled in mapping is based on your data collection. So when you send your survey team out to the field to collect data, they have a certain level of accuracy expected of their data collection, and that leads directly into the level of accuracy that you can achieve in mapping. But it's actually really the reverse relationship. It's important when you're designing your data collection process, right? We talked about how the process of GIS works in identifying the questions you're going to be trying to answer, in identifying your potential data sources, and designing your plan to move forward with that. Starts with understanding the use to which this data is going to be put, or this mapping environment. And that controls the level of effort that goes into the data collection and mapping. And I should find a different word to use for that, because I mean mapping in the sense of collecting survey data versus mapping in the sense of presenting it in a map. They are a symbiotic relationship. And the way that we describe accuracy in a mapping context is a little bit different than the way that we describe accuracy in surveying. So in mapping, your accuracy in your identification of a feature and the location of a feature on map has to do with the scale at which the map is displayed, right? Something might look perfectly accurate at a very zoomed out scale, and when you move in closely, you find that the little dot of where they put Juneau isn't actually in Juneau, it's nearby, but you're looking at the map on a different scale and it didn't matter that scale. So understanding that accuracy standard and the relationship to scale is important if you need to define that sort of thing. So this is the best example we could find on a mapping standard, and this is a really globally applied mapping standard because it's part of that national map project. So for horizontal accuracy, the description is that not more than 10% of the points tested shall be in error by more than 1/30th of an inch measured on the publication scale. So what does that mean? If you're plotting a benchmark or other known point on a map and you show it at a scale greater than 1 to 20,000, it has to be accurately plotted within 1/30th of an inch. So potentially something that might seem difficult to measure or relate to, except that we're in the GIS environment, and that's exactly what we get to do, right? We can measure things, we can do spatial analysis, we can grid an area and make sure the points fall within the grids that they're supposed to fall within. And we do that using known coordinates of known positions like benchmarks, property corners, things that have been identified as unlikely to move and change and have had a survey coordinate precisely applied to them. And the level of precision is related to the level of accuracy that you're expecting of your map. Similarly, there's a standard for vertical accuracy. So when we're talking in a 2D environment, vertical accuracy is a little bit harder to define than I might do, for example, for sonar data collection. I'm going to define it in much the same way that I do horizontal accuracy because I'm looking at things in 3 dimensions. So I'll expect an accuracy of a depth in the water based on a known water depth. So I'm going to compare it to something that I've measured directly using an independent system. And I'm going to expect a certain level of accuracy in the Z dimension, which is typically your vertical. For the vertical accuracy of a map, the way that we identify accuracy standards is based on a known elevation within a certain horizontal distance, because sometimes you can get vertical accuracy problems simply because you have a horizontal shift in your data. So you may have exactly the right vertical elevation, but you've plotted it 10 feet in the wrong direction, and therefore it's completely inaccurate. So there's a relationship again between vertical accuracy and horizontal accuracy that we have to understand. So for the national map accuracy standard, that is to be not more than 10% of the elevations will be in error, and there must be a scale of acceptable error because no elevation that we measure as human beings is ever perfectly accurate. By more than 1/2 of a contour interval. So if you know an elevation at a certain point, that elevation must be correct within 1/2 contour interval of that known point. That way, if you have known elevation points sliding around on your map because your map is not accurately placed horizontally, sometimes that's identified through a vertical problem. And you can often see that when you place 2 different data sets over each other. It might look like one of them has an elevation shift when it's actually a horizontal shift. That's a pretty common issue that we see in measuring shorelines, for example. It might look like your shoreline depths are all too deep or too shallow by a foot, and really what it meant was that you shifted your slope horizontally in the wrong direction, and it looks like a mirror of the correct slope in a different place. So I hope that makes that clear to visualize. And then in addition to the positional accuracy of your information, you have the thematic accuracy of your information. So if you have incorrectly classified something or incorrectly identified an object in your data set, then you have a problem of accuracy in your data. So again, if we look at GIS as a means of interpreting and sharing information with somebody in a spatial context, there has to be a recognition that there's a potential for error in our interpretation of the real world, right? We're taking real world objects and we're turning them into spatial entities. So if I've identified something as a wetland that is not a wetland, then my map is just as inaccurate as it would have been if I put that wetland in the wrong place. So that leads back into the whole process of designing our data collection project and our mapping project to meet an intention, and then collecting our data and going through revision and QC to make sure that we have accuracy so we can accurately represent this information to our viewer. So you start to see how this all ties together, right? If we miss any piece along this puzzle that we've gone through 15 lectures now on what seem like really wide-ranging topics, they really all boil down to accurate representation of ideas in a spatial context and an informative context. So it's kind of an exciting time, or really an exciting time, but also a sometimes terrifyingly huge amount of information to absorb in GIS and survey and geospatial information, because the technology is evolving so rapidly. You often see people talk about the development in technology on an exponential curve, and so it just is going to continue to accelerate throughout your careers and your lifetimes. And hopefully that seems like an exciting prospect. Sometimes it can be a little daunting because there's that constant need to learn new systems and new ideas. So you can imagine what it felt like to the people that have been doing hand drafting all their lives that suddenly had to shift into a computer aided drafting world. You're going to see similar changes throughout your career. And we're going to touch on a couple of the big ones today. But some of the cool, flashy, exciting ones are in data collection. The development of modern robotic technology has completely modified the way in which we are collecting data. Just in my brief career, the technology that's used and the way that it's implemented is totally different than it was when I started 15 years ago.
So what was that picture on the far right about? I could tell, so on the left, it's obviously probably satellite imagery. Then we got handheld GPS and what I'm guessing is LiDAR dronage. But what is the right picture used for, or what does that represent? It just looks like some camera footage.
Yeah, so I admit that I didn't select that photo. To me, it actually can represent a few different things. You can see the construction going on in the background, and GPS positioning of construction is also a rapidly evolving field. I've worked on a couple of projects over the years where we put really precise spatial positioning on dredging operations or other types of construction pile driving operations. So we're actually now integrating GPS into those operations to make sure that things are done according to the design. But then there's also the construction monitoring part of that, and a lot of the technology that we talked about was that last class, looking at the different tools that Esri's been rolling out for data collection out in the field. And I think that's one of the areas that they excel over other programs, maybe not over like Trimble and some things like that, but where you send your data collection, or you do it remotely now. More and more of these types of operations are being done by remote observation, and analyze that data and information back in the field, or back in the office.
Gotcha. So it's like representing that you're probably using a lot of these instruments in the other pictures in construction and stuff like that, kind of.
Yeah, so our company pretty frequently, construction management is a big part of the engineering process. After you engineer something, you serve as the owner's representative to make sure that things are built according to the standards that you developed. And so we pretty often use cameras in that environment. And part of it is this neat, flashy whiz-bang thing that the client gets at the end. They see a video of their dock appearing out of nowhere or over time lapse. But it's often incredibly informative about the process of that construction. And that type of technology is actually being implemented in things like offshore pipeline development. So you have real-time construction monitoring of positional information, or you might have a remote camera down there on the bottom of your crane operating, and those people used to be on site reviewing that information, and now they sit back in an office or a shoreside trailer. You no longer have to send people out in the field. One person can sit there and monitor 5 different projects and that remote data is coming back along with the positional information. You know, say you've got a little mini sub out there with data collection. That's one thing. Mapping has really rapidly changed since I left Terrason. They started doing a significant portion of their NOAA charting projects with drone operated survey systems. So they still go out typically with a ship and do their normal bathymetric survey operation, but they have maybe 1 or 2 remote operated submarine vehicles collecting data as well, or water surface vehicles out there collecting data. So with all this technology, we're rapidly working people out of jobs, but hopefully in that sense that it will someday be the robots doing all the work and we get to lay around in luxury. I'm not sure, but it's important to embrace the technology rather than run away in fear, because it's gonna show up no matter what you do. So again, it's been a really rapidly evolving field, so embrace that would be my recommendation, and continue to learn new things like you're doing right now. So just an example of a fancy new survey technology. Looking at this now versus, I think I rented one, gosh, it's been 8 or 10 years. This was the newest, most amazing thing on the market. And you can't like buy them off the shelf anymore, but they're getting to be common enough that these are being applied in just like building management systems. So I want to understand how my skyrise building is being operated, and if somebody changes their floor plan, I want to have an understanding of that. And I'm going to take this incredibly powerful military grade technology and drive it around the building. You can imagine it's only a matter of time before it's like my Roomba that goes around and vacuums when I'm not paying attention. These things will go out and monitor infrastructure, and they will do it with precise accuracy. So maybe someday that's how we refill the cartridge in a printer. Some little drone flies in and it knows what to avoid because the area has been precisely mapped, and it fills your printer cartridge for you. It doesn't really take a far stretch to get down those thought processes, because our technology is already developing quickly enough to allow that sort of thing. So maybe instead of being surveyors, we'll all be the delivery drone designers someday. So one piece of all of this new data availability, all this new GIS process, is new sources of data, higher accuracy data, higher refresh rate for temporal information, and the miniaturization of these systems. So they are now being deployed all over the place. We don't even see a significant part of it, and it's all sending information back to people that are putting that data to use. You can probably imagine where this all leads to at the end of the lecture, which is understanding privacy and how we put this data to use. Right now, we're in that stage of rapid development, so that you have this race of developing the technology, and I think there will be a stage of figuring out the ramifications of a lot of it later. But obviously, you couldn't have a driverless car if you didn't have a highly accurate map of your road system. So if you can imagine trying to use a driverless car when Google Maps first was available on an iPhone, when it was terribly inaccurate, versus the level of understanding that we have of our road systems now, where a driverless car is going to have to know where construction is happening, where traffic jams are, where weather systems are unsafe to travel. So all of that information is now being updated much more frequently. And all of that comes back to data centers and people that are using it. Otherwise, it loses its value. So having been alive, all of us, in the last 10 years of smartphone development and seeing how rapidly that's changed the way that we interact with the world, this understanding of the value of location-based services is probably pretty universal these days. Having a phone that reminds you to do something when you get somewhere, or having technology that reads the conditions around you and adapts to that. A lot of that comes back to that positional information on your phone. So I don't know if you've played with your Google Maps in a store, but I think the Lowe's on Tudor has an internal store map, or at least it did at one point. You can actually look at where the shelves are when you're in the store, depending on whether or not you have a good enough cell signal. So that kind of information is becoming almost micro in its scale, because people are interested enough to go out and map that information and provide it to the public. And maybe someday you won't have store clerks anymore. You'll just ask your phone where to find something and what's on special, and it will know and tell you. Just like if you've ever used the app Zombie Run, your phone will tell you where the zombies are and when they're coming to kill you so that you can run faster. And that's technology that wouldn't exist without a computer that you carry in your pocket that knows where you are and where you can go. And that all ties to a GIS system somewhere.
Are you an active user of that technology, Professor?
I am not a runner, but I am terrified of zombies. So I think it would probably be an effective way to cure my not running problem. There's another version too. If you're not, I'm kind of squeamish where zombies are concerned. So there's some other that are more like goal-based. So if you're a goal-based person and you like problem solving, and you need that little kick out the door to get exercise, but aren't ready to play, what's the game that all the kids play, Pokemon Go? I lived kitty corner to a Pokemon Go point in Airport Heights. So there's another thing we can thank Google Maps for, is this sudden, not really influx, more of an outflux of young teens going out and apparently actually getting healthier in the process of chasing around a GIS construct, right? They don't know that it's a GIS construct though, or it wouldn't be cool probably. So this is supposed to be talking about the future, but like I said, a lot of this is already here. We're just seeing how things change and get implemented over time. I have noticed lately, it seems like possibly Google Earth is sort of dying in its development. I haven't seen a lot of new changes. They have added some new features, like you can do world tours, you can learn about new systems, but they removed the photos aspect of Google Earth just recently. So I'm not sure where they're going with that technology, but it's something that I use pretty heavily in my work. And of course that all feeds in to Google's Maps system, which is what is more generally used by the public for finding everything. I don't even go places in Anchorage anymore half the time without Googling something that I definitely don't need to do, but it allows me to unplug my brain from the problem of getting from A to B if my phone tells me how to get there, I guess. Sometimes it feels like a handicap, but so that's, again, an example of data sources from around the world. A lot of this information is crowdsourced, especially if you start looking at the buildings built into Google Maps. There's some neat stuff. I saw somebody constructing fuel silos at the refueling station for the McMurdo Ice Science Center. People go in and they develop 3D models of buildings so that you can interact with the world in a 3D context within Google Earth. So that's crowdsourced information, right? If you update a location or information about a business in Google Earth, you're participating in a crowdsourced GIS system. And we're starting to see more of that brought into the Esri environment. So I've got you guys building an Esri online project because I want you to be aware of the resources that are out there, first of all, that you can take advantage of in your own projects, but also this new kind of community of information where instead of having these GIS silos where each business maintains their own data and the data that's available to the public is all paid for by their tax dollars, we're building now communities of GIS. So this is a great example. It's a brand new, just been developing over basically this semester. I'm not exactly sure what day it rolled out, but it's already far more information than it was when I first looked at it a couple of months ago. I kind of wonder if some of that's driven by the COVID-19 need for data, right? We all are craving data and information, and a huge amount of that data is spatially referenced and being built up in our ArcGIS portal environment. So this is the state's new open data portal, geoportal, and it has state agencies, local cities and municipalities, and federal organizations. And I believe they're working on rolling in nonprofit and other special interest groups information so that you can actually soon have a single source of all that data that I gave you guys in a spreadsheet that I've collected over 15 years. It's just going to be on the geoportal. So it's going to be kind of like, you know, how it is when we tell kids these days about how you used to use a rotary phone. They're not going to have any concept of what that means and why that's different than going to the open data geoportal. And that's one of the goals, is to universalize the data and get it available and get people communicating. Obviously, there's going to be some drawbacks to that. You might miss pieces of information that were specialized in their implementation because they're not important to the group as a whole. But overall, the level of access to the data is going to increase exponentially, especially as Esri makes some of their basic functions available to people for free. So in reference to the getting things for free, a free Esri account gets you some access to their online ArcGIS online and their online sharing of information. I'm not sure, there are a couple of other, I think, open source attempts at this, but with the volume of data storage that's involved, I don't know how that will evolve over time compared to a commercial environment like Esri has. But so you have two components to the Esri online portal. You have the data sharing, right, that we've started to look at for all these data sources, and the storyboard presentation of your data. But there's also the cloud computing component of it. So you can build basic maps and put things together, but you can also run some of your data analyses right within ArcGIS online and have that happen in a cloud computing environment and have that information available to you in your mapping account. So that's functionally maybe not that different than what we're used to seeing, but the infrastructure now is shifting in a different direction, which has a lot of interesting implications to how this might become more accessible to more of the public. and become a little bit more routine in use, right? If I don't have to buy a $1,500 ArcGIS license to manage GIS data, I'm a lot more likely to get involved in a non-professional capacity. So I think that's one thing to watch for the future, is how that changes the way the public perceives GIS. And always that shift in public perception is the trigger for a lot of development, because new people look at something with a different perspective, and you have really rapid development from those ideas. So it's kind of frustrating at times because it's so limited compared to the data analysis capabilities that we're used to in ArcGIS or similar software, but also very exciting in the human component of that. So again, this is an example of an ArcGIS online community that you guys are now part of because you've published to our group, hopefully, for the lab that was due today. We're doing it in a sort of subversive private group way, if you properly set the privacy on your assignment. But now you have the mechanics of how you can go out and access this data and use it. And if you have a project that you want to share with the public, this would be how you would go about doing that. Again, the sharing of data sources is becoming really impressive, and that's one of the way that Esri captures people. There are some similar services out there through other software. I tend to use Global Mapper quite a bit when I want to look at background imagery, because they have a huge selection. I think almost all of these are similar to ones that are available through Global Mapper, and the imaging processing within Global Mapper is really powerful. I don't like the way that it handles symbology quite as well, so I don't use it for mapping, but it's a really great way to analyze your data. And then there are some similar open source projects. OpenStreetMap was originally, well, I don't know if it was originally developed within QGIS, but it was developed in partnership with a lot of the same people. And it's essentially your own Google Maps that the OpenStreetMap community has developed in one of these open source projects, which I'm always really impressed by the people that contribute to those, because I never feel like my programming is up to par to help, but maybe in this sense there's other ways to contribute to projects like that, maybe through mapping experience. So and then the Esri Living Atlas is another extension of this idea that someday in the future there will be just huge amounts of spatial and temporal information available to everybody. And you can see just by what people have done with some of these in your perusal of different story maps and source data, how really effective this is already. And it's really just beginning. So another wave of the future is understanding how our global environment is integrated. So this is a visualization of a Twitter mapping. So these are Twitter sources that are being reshared, and how that is spread over a network. And it could be a global network, right? This could be something that's shown as, locations, if you know the locations of your network of whatever you're trying to express, or it could just be a idealization of a network in the sense that we are all points within this shared information, and this is how we interact. So there's potentially a lot of different systems that could be modeled in this way. We often use 3D GIS modeling as a way to get at understanding of systems and structures that aren't necessarily in a specific geolocation. You know, I might want to understand how a flow environment works and not necessarily care if that flow environment is in India or in Pakistan, or no, I was trying to pick two very different places, which they are, but not spatially very different. Anyway, India or Guam, you know, it's still a spatial representation of your network and your data and your information, but not necessarily tied to the globe. But the technologies that we've developed through GIS systems lend themselves really well to that source of spatial data analysis or networking analysis in a way that our brains are already kind of pre-programmed to understand. So some of these are presented as unsolved problems, and some of this is because this is obviously you know, building on previous lectures. The rate at which things are changing is so rapid that some of this is no longer exactly true. So we've begun to solve some of these problems. So the idea that we could represent geospatial information in real time, which is essentially what they're talking about here, the integration of geospatial data across time and space. When we're using remote sensing technology, like the description I gave you guys of a construction project, if that's showing up within my data analysis at the moment at which it's occurring, and I've had sufficient time to model the way in which it's going to come in to me, I can look at the effects of that data in real time, right? So if I'm just getting a stream of data in a non-identifiable context, it's not going to benefit to me that I'm getting it in real time. But if I'm getting a stream of data and I have in some way predicted how I'm going to present that information, then I can build something like a model of how that's happening in real time. So apply that to weather. Like if I understand what it's going to mean if I see different temperatures in different places and different humidity and wind sensors, I can take that in and I can visualize a model of cloud movement or other barometric measurements and present that information in a way that's understandable to a human looking at the screen. So if you can imagine all of the processing that went on to get to that point, right? I have measurements coming in from around the world, or at least around my area of interest. And I have understood and modeled the system well enough in the past that I can now build this real-time means of telling people what that information all comes together to mean. And we got there through a series of spatial analyses that I'm now automating well enough that they just appear in real time and it looks like magic. And really it's just a string of zeros and ones that came around from those sensors that I set out on little buoys in the water and stuck to the side of buildings and pulled all that information together. And now I'm gonna show people in real time this tornado that's destroying this nice little town in Texas. And I'm going to predict when it's going to hit Louisiana. And that information then becomes a valuable source for people to make choices about their lives. So it's a pretty powerful information tool. And a lot of that obviously is still in development. The application of it to weather is a pretty familiar environment, but there's a lot of different ways that we can start putting that power of analysis to work for us. So some of that can be deployment of, we talked a lot about delivery systems or maintenance systems going out into the environment. Our municipality maintains a whole library of different maps about things like crime rates, or you can go look up support infrastructure for people who need to be in nursing homes, or other information like that that's now available directly from our municipality to us. Those aren't necessarily things that they're updating in real time, but in a larger community, some of those things could certainly be updated in real time. If you have COVID testing centers showing up in different locations on different days, you're going to want some way to easily update that information to the public and get it out there without somebody having to sit down and collect all of that data and bring it in and understand it and QC it and put it on a map, because by then it's no longer applicable in that application. Let's see. So one of the things we didn't get to play with yet is the temporal aspect of ArcGIS Pro. I have gotten at least one question about this. So this is where you take your mapping information and just like in Google Earth, you can go back and look at older aerial images. You apply dates to all of your information, so you can look at a snapshot of your map at different points in time. And there are so many different things that you can do with that. Then now you've taken your 2D map and you've added a temporal dimension to it, and you can watch that change over time in sort of a time-lapse environment. So again, these are identified as unsolved problems, but a lot of them we're beginning to solve them already. So we do have the capacity now to do temporal mapping. I don't think that we've fully realized what it will mean to work in a fourth dimensional environment. I think we'll see new ideas coming to that as more people get involved in that type of mapping. But the basic capacity is already within ArcGIS Pro. The concept of automatic change detection is already put to work. We have sensors out there on infrastructure to notify people if there's infrastructure problems. So maintenance crews can be dispatched using their ArcGIS dispatch technology or other substitute. So all of that information isn't, may not be exactly real time, but it's not going to happen exactly the way things used to happen. And so I think we'll start to see that developing as well. And obviously, when we get to the point where we start using automated delivery systems, we're going to have a much more timely update of information about things that might impact those delivery systems. So I've kind of hinted at the problem along the way of privacy issues and a loss of anonymity. We've all been coming to terms with that and experiencing that over recent periods in the web. We like to imagine that we're this anonymous person out there on the web interacting with data, and we tend to forget the fact that all of our activities out there on the web are being tracked. We've all been tagged. There's some data repositories out there of our behavior and our patterns. I now get notifications of new Vibram shoes on almost every website that I go to because I bought a pair of Vibram shoes at the beginning of the summer. And the more that we interact with the digital world, the more we begin to lose our privacy. And I think one of the trade-offs of that is obviously the more information that's collected, the less meaningful it is to any specific person until there's a reason that they need to pick you out of the crowd. So there's going to be costs and trade-offs to that, and we're already starting to respond to that within our legal framework. But it can be really shocking if you actually sit down and talk to lawyers about how we respond to misbehavior and new technologies that our legal system is just not designed to address. So they may be able to destroy your life in a digital environment with no repercussions because there's not a law in place. So it's kind of key that we understand that if I've now given a digital device the right to track my spatial movement, that could have some implications. So this is something that we talked on earlier in the semester, and just another example of things to look forward to in GIS and mapping and survey. And that's this updated set of positioning information. So we talked about it in the context of the state plane zone, but we also talked about where this all came from. So we've developed a new model of the Earth that has allowed us to better position ourselves spatially on it. So that development of the model is partly driven by all this new information. So we have sensors out there collecting information about the movement of the Earth's plates. We have whole networks of systems collecting information about tides. So we can now understand how the interaction of the tides with the plates changes positions of things relative to that system, and how that affects our ability to model the geoid, which, as we discussed, is not a sphere, is not an ellipse. It's this imperfect ellipsoid system that's affected by a lot of different actions of our Earth. And none of it is stagnant. It's changing over time. So this new model becomes more accurate because we have collected all of this other data that goes into the model and recognizes that these changes over time, and will now allow us to much more specifically position things on the Earth and move us closer to this concept of being able to send the robot to deliver coffee to my mom on the other side of town, and not having to be involved in driving that because it essentially now has its own brain and its own eyes, and is better aware of the world around it because we have a greater level of understanding of that world. So maybe an overly dramatic way to say, watch out for the 2022 state plane zones, but it really all is an integrated system. So the better we have data coming into our model, the better we understand that model, then the better we can present it to those who are using it. So recognition of the fact that this is an ever-changing system. What you learn now is light ages away from what I learned in my first GIS class, and it will only continue to evolve.